So hi everyone, today we're going to talk about, it's a second lecture about the neural networks. So today, again, we are going to follow the chapter in Efron Hastie 2016, the book Computer-Age Statistical Inference, Algorithm, Evidence, and Data Science. And a very important reference is Professor Kuan, Zhongming Kuan's paper on the Palgrave Dictionary of Economics, Artificial Neural Network. It's a review paper Kuan's written in 2008. And another really important reference is the book by Chollet, which name is Deep Learning with Python. And yes, which means that we're going to apply the Keras package in Python today. So this is the problem we are going to deal with. It's called the handwritten digit problem. Okay, so if you read the book by Efron and Hastie, they said neural networks, which had been a baby for decades, and he really cut their baby teeth, 他们把他们的乳牙拔掉 until they work on the optical character recognition test, aka OCR, which means that we want to teach the machine to recognize the handwritten digits, such as numbers, as in zip code. 就像大家看到，在邮局，你可能希望你的机器帮你认邮递序号。Or maybe if you are driving, you may remember that when you want to enter any parking lot, on the entrance there will be a camera there, try to recognize your steel plate. 你现在去开车的时候，所有停车场门口都有车牌辨识系统。They want to recognize the number on your steel plate, and that is use the same technology as what we talked about the deep learning, the neural net. So here is the data set we are going to use. It's called NIST. So NIST stands for the National Institute for Standard and Technology, or 美国国家标准局. So they had such a database to collecting hundreds of thousands of handwritten numbers. Okay, and M here stand for modify. So in this paper, Lacan et al. In 1998, they pick up 60,000 images out of that huge database as the training set, and another 10,000 images as the testing images. So we want to teach the machine to read the numbers for us. And ideally, the machine can tell that this guy is 5, this guy is 0, this guy is 4. Which is maybe a simple task for humans. So I believe everyone in this classroom can easily tell that, although this guy and this guy looks really different. Let me say it again. This guy here, the third in the first row, and this guy, the last one. Although they look pretty different, and everyone can tell if they are 4. Okay. If you see different numbers, please let me know. Okay, so there are 4. And this guy, although this guy goes from the top right hand side, from the northeast to the southwest, like this. And this guy goes from the northwest to southeast, like this. But both of them are 1s. Yeah, it's easy for humans. We can tell which numbers it is. Okay, no matter the 4 written like, the 4 look like this guy or this guy. No matter the 1 looks like this or this. Okay, but it can be a difficult task for computer. When we have an image like this, the computer will interpret it as a 28 by 28 matrix. I'll show you guys some the matrix in minutes. And if you want to input some matrix into the computer and want the computer to recognize the number, it can be pretty hard. So here are some early days research about this. Okay, so we humans are pretty good classifier. So these numbers are reported by CMART et al. 1993. Okay, so there are test error rates. So the error rates for human eyes were 2 to 2.5%, which means that out of 100 images, humans, we may make 2 or 3 mistakes, but we can recognize most of them. Okay, that's humans. Okay, how about we consider those 28 by 28 matrices as 28 by 28 different variables and fit a linear regression model or a linear classifier, which Lecan et al. Did in 1998. If we have a linear model, then the error rate will be crazy, like 12%. In fact, it's not so bad. So 12% is not so bad for a linear model, but of course it's way worse than humans. And Lecan et al. 1998 considered several different methods. So they consider the neural networks. The error rate were around 4.7 to 2.5. Okay? And believe it or not, for this single model, they spend, make a guess, how much time they spend to train this model. If the Wikipedia is right, then Wikipedia told me that they spent 3 whole days just to train this one single model, and which made error rate even worse than humans. So I'm just happy that I'm not the one who wastes 3 days. And there was still something they call the convolutional neural nets, or CNN. We'll talk about it today. So it's another version for the neural nets, and it did a little bit better. The error rate was 1.7 to 0.7%. So note that, okay, the ordinary neural nets, the feed-forward neural net, has error rate worse than human beings, but the CNN, convolutional neural net, had a better error rate. That's good, okay? So yeah, machine can do better than human in this case. But they also tried something we will not talk about in this course, but there was one important method in 1990s and 2000s, the support vector machines. They also tried support vector machine, and which the error rate were 1.1 to 0.8. In other words, support vector machine did way better than neural nets in 1990s and 2000s. And you can see those 4 are results reported by Lecan et al. 4 years later, Durlauf and Chollet, they tried the support vector machines again, and they reported some error rate around 0.68 to 0.56%. Way better than those numbers, 4.7, 1.7, anyway. So that's what we talked about last time. So neural net was kind of popular around 1980s and 1990s, but totally silenced around 2000. Because around that time, people realized, first, given the computing power around that age, to train a single neural net model can take you a long time. 3 whole days using a supercomputer. And after so much work, the performance was worse than other methods such as support vector machine or some other methods I talked about before, the random forest or gradient boosting, for example. So around 2000, the neural net were totally outperformed by other methods. But around 2010, reincarnation. So with some fashion name which is called the deep learning, people realized that, okay, first, around 2010, we got better computer, better than 1990s. So we can spend just a little time to train a good model. And you can see with the help of the computing power,
these were the performance of the new neural nets. So in 2010, Keras and L reported that their test error rate was 0.35%. Okay, and if you consider the convolutional neural nets, Keras and L 2012, they reported 0.23% the test error rate. Okay, there are something we want to talk about, some details we want to talk about this data set. So NIST, the National Institute for the Standard and Technology, they had this kind of database about handwritten digits. Okay, so in fact, they have several different databases in. Okay, and so traditionally, people used to use the database number 1 for the training and database number 3 for the testing. What happened to database number 2? I have no idea. And they realized that, when you try to train this model by this way, use database number 1 for training, database number 3 for testing, all algorithms perform pretty bad. Then they realized what happened. The database number 1 were some digits written by their own employees. 他们请公务员写了很多数字 around 50,000 different digits. And database number 3, they ask high school students. 所以他们的 database number 1是公务员写的数字，他们用公务员写的数字来训练 model， 让他们辨认高中生的鬼画符。So in early days, people realized no algorithm work in this case. So that's what happened when we have the modified MIST. So they want to merge those two databases together, and so we have in this database we have some well-written digits written by employees and some graffiti written by high school students. Anyway, so another detail about it is that nowadays when people talk about the neural nets, some people also call it a fancy name, deep learning. And something about this. First of all, deep learning, the name is cool by itself. 你用中文讲就更酷了，因为中文叫做深度学习，就是我已经过了那个年纪很久。不过，如果你现在认识一个新的男孩子或女孩子的话，你都很希望别人说你很有深度。Yeah. And when they call itself deep learning, which means that it implies that all the other methods were shallow learning. One reason it got so popular, but anyway. So this is about the database, and this is about Python. So nowadays there are several different packages for deep learning. And Python has become kind of standard in this kind of test. So we're going to do some Python. So if you have some experience in Python, it'd be great. If not, then there are some tips. So first you have to install Python, of course, but the easy way for you is to install Anaconda. So all you need to do is you go to just Google Anaconda and click on the first link, and you'll find out this is their website. And in product you find individual edition. And it goes down and down. Press download, and it goes very end. It depends on if you are a Windows or a Mac or a Linux user. So, and my suggestion is to install the Python 3.7 64-bit. After installing the Python, and in the start menu, go down and down, you'll find out your Anaconda 3 here. And you'll find something called the Anaconda Navigator. Click on it, then you'll see this guy. So that is what we're about. Let me go back to slide for now. So, yeah, that's it. First thing you need to do is to install Anaconda. And some patient when installing, the Anaconda will ask you want to install it just
just me, which means that for one user, or you can install it for all users. Okay, people have realized that, okay, don't do all users, do just me. Two, all users might lead to different problems reported by different people. So when installing Anaconda, click on just me, unless you are pretty good at computers. After that, launch Anaconda Navigator. You'll find something like this. And so we want to install the package Keras and TensorFlow. So an easy way to do that is go to environment. And here, select all package. And you may want to click on the update index. Then your Anaconda Navigator will show all the packages which are installed and not installed. And after that, search for TensorFlow here. I don't know if you guys can see. Search for TensorFlow and you will find several packages are about TensorFlow. Click on Keras and TensorFlow and press apply here. Let me go back to my slides. So find the list all, click on update index, search for TensorFlow, select TensorFlow and Keras, click on apply. Wait for a few minutes, click on apply on the install package window. It may take a while for the packages to be installed. After install the Anaconda, after installing the packages, go back to your navigator, select the home again, and launch something called Spider. This is the thing we're going to use. If you have no experience or very little experience on Python, that's what you are going to do. If you know Python, then you may have your own way to work on everything. Then that's it. Okay. Okay. Now this is your Spider if you do everything here. So, many lines of my code are from the book written by Chollet. So I listed it here. So first thing you need to do is want to load the package. So you can select the line, or you can just put your mouse here and press either F9 or select list. Or you can see here is some image here. It means run selection or current line. To run it, then we install the MMIST database from the Keras package. And then we can read the package. So now I define 4 different objects: the chain images, chain labels, test images, test labels. So the chain images contain 60,000 of 28 by 28 matches, and the labels indicate like which number they are. So if you are very confused, we can take a look at our data. So here I want to show you the first 10 chain labels. So, and you can see the output here. They are 5, 0, 4, 1, 9, 2, 1, 3, 1, 4. This is the labels look like. And if you want to take a look on the image, we will import the package called the Macmillan. So again, you can download my py file in NTU Kubo. So if you like, you can work on it by yourself. And so then we can take a look on, for example, we can try this guy. Our image number 0, and we run this part, and the result will show up in the plot. This is our image number 0, so it is a 5. And we can try some other. For example, this guy is image number 2. This guy looks like a 4. Okay. Okay? Now, here's the deal. For human beings, it may be easier for us to recognize, okay, this guy is a 5. This guy is a 4, so this, I don't know. Usually we don't write 4 like this, but this 4 looks like what you see in your calculator. So somebody like to write a 4 like this is okay. But for humans, it's easy for us to recognize those things. But for computer, this guy is just something like this. This is a 28 by 28 matrix. Lots of them are 0. Here, 0 means that at least pixel it is white. Here are some huge number. 220, 222, 245. So each element should be some integer numbers between 0 and 255. If 0 means that pixel is white. 255 means it's totally black. And numbers between 0 and 255 means it is dark gray or light gray, something like that. And anyhow, what we're going to see is this is a huge matrix, like this. And we want to ask your computer to generate a model to recognize what it is. That is why this task puzzles people for decades, since the late 1980s to the early 2000s. Okay, so this is the problem we're dealing with. Let me go back to my slide. So after installing Anaconda and Keras, you can just input our data set and work on this. Yeah, I'll follow my codes. Okay, so before working on your model, the first thing is, can you guys see my codes here? Okay, thank you. The first thing is you want to rescale our inputs from our input were 0 to 255. We want to rescale it into between 0 and 1. And our labels are numbers 5, 1, 2, 3, or 5, or 10, or 7, and like that. We want to relabel our labels to categorical variables. So here, these lines, we want to rescale our image. First, they were 28 by 28 matrix. We want to turn them into a long vector. And second, we want to rescale it to between 0 and 1. So we reshape it into 28 by a long vector. And second, we divided everything by 255 to make them between 0 and 1. Okay, and we also relabel our labels. So first, we import the two categorical function from the Keras style utils. Then we apply them. So we can have a look on the labels. So before the two categorical function, our labels are this. So this, the image number 0 is 5, image number 1 is 0, image number 2 is 4, image number 3 is 1, something like that. And after working on this, our label become, I want you to be able to see both windows. Yeah, this will be okay. So the image number 0 is 5. So we label it as a 10 by 1 row vector. And 5 is 1, others are 0. And again, image number 1 is 0. We reshape it into a vector with 10 dimensional vectors. Number 0 is 1, others are 0. Image number 2 is a 4. We reshape it into a vector with number 4 is 1, others are 0. That's what we do. Okay, here are some technical details. And here is our model. Okay, first we import the models and layers. And in this part, I set up the model and I'll just set up it and I'll show you guys what it is. Okay, so this is a very simple model. This line here means that our input is a 28 by 28 vector, and we have 512 neurons, 512 hidden units, and the activation function is rectifier, RELU. And our second layer have 10 neurons. This is our output, and we use the softmax activation function. So this is a 3 layers neural net. We have the input layer, we have one hidden layer here, we have the second layer, we have the third layer, which is the output layer. And our input is 28 by, it's a long vector, which it has, let me see what numbers it is. Our input is 784 by 1 vector, and we have 512 neurons. In each neurons, we have weights for 784 input and 1 bias. Let me say that again. In each neuron, we have 784 weights and 1 bias. So we have 785 parameters for 1 neuron. And we have 512 neurons. So in this single layer, we have more than 400,000 parameters. In the second layer, we have more than 5,000 parameters. So in total, this is the number of parameters we have. Okay. So stop me anytime if you have any question. And this is our model. And to work on Keras, some key point is want to specify the compiler, which has 3 elements. So I'll begin with the letter. The matrix is accuracy, which means that after work out everything, so your program will report the accuracy. And our loss function is the cross entropy, categorical entropy, and we use something called RN. SPROP as our optimizer, which is a family optimizer, which is a little bit different from the stochastic gradient descent we talked about last time, but we'll try this later altogether. So, after import this guy, we want to train the model. So, in this model, remember we talked about we can do the batch by batch training. So in each run, we only consider 1 batch of data, and our batch size is 128. And we'll do 5 epochs together. Remember, in the beginning of this class, I said it took Lecon et al. 3 whole days to train such a simple model, and we can train it all together. So it takes 4 seconds for the first epoch, another 3 seconds for the second epoch. So in total, 16 seconds. So from 3 days to 16 seconds. Okay, that's the technology. And our in-sample accuracy is 98.83%, which means that out of 100 image, our codes make 98.8 correctly in average. We can also ask our program to try on the test data set. It goes like this. So our out of sample, this is on the testing database. Our out of sample accuracy is 98.01 or 98.02%, which means that our test error rate is less than 2%. So remember, the test error rate for humans were around 2 to 2.5%. So after this 16-second training, we're doing better than humans. We can also take a look on some. I just want to show you guys. I want to show you guys. Okay, I asked my program to list everything they made a mistake. So for example, they made a mistake on testing sample 115. It goes like this. So this guy. So this guy, our database said it should be a 4, but our program recognized this guy as a 9. Another guy will be this. This guy here. Okay, we made another mistake on this one. So. Okay, this is the 7, but our program recognizes this as a 2. I don't know, I think this is an honest mistake. Okay, this is it, it's all about. Let's go back to our slides. So here I put everything here. So as I said, we just set up a simple model with 3 layers. In the first layer, we have 512 neurons, and the second layer, we have 10 neurons. We use the ReLU activation functions in layer number 2, the hidden layer, and we use the softmax in the output layer. And so our output will be a probability between 0 and 1. After setup, and to do the Keras, we have to set up the compiler. We have several different ways to optimize this, to minimize this loss function. And nowadays, people like to use RNSPROP, which was proposed by Geoff Heaton in 2012. Something famous about this algorithm is that Heaton never bothered to publish this guy, but it works so well, and now people use it a lot of time. And here is our loss function, which is the categorical cross entropy. Yeah, I believe Kuan talked about this when he talked about the regression classification tree. So this is our performance. What else? So let's take a look at our model again. So here we consider a very simple model. We only have 3 layers.
first they have 512 neurons. The second, the input layer has the 10 neurons as the output. But even in this simple model, we have more than 400,000 parameters. It will be pretty difficult for us to train this model, but it's done. It is done anyway. And we can try something different altogether. For example, here we try the Rman SPROP. So we may also try the stochastic gradient descent we talked about in the class. So if I try this as SGD, and I input everything again, and I try to train the model again. So it may take another 15 or 16 seconds. So the in-sample error rate is around 10%, so still okay, but not so good. And we can also try something called add-on, which is another modified merge version for the stochastic gradient descent. Yeah, so it's done. So by doing add-on, again, after 5 epochs, the in-sample error rate is almost only 1%. And we can take a look on the out-of-sample error rate together. So we use the function network is the name of our model. We use the function evaluate to evaluate the error rate. So the out-of-sample error rate is around 2.1%. Again, pretty well. Yeah. Sorry. So here are the results if we use the ReLU. So we may also try sigma function, for example. So here are the results for sigma function. And again, so it performed a little bit worse than the ReLU, but not so bad. And before working on this, I was expecting it may take a longer time than the ReLU, but yes, it's almost the same time. And finally, here are the results if we try only 5 epochs. We can also try more. For example, we can try 10 epochs altogether. So it may take us around 31 seconds. Okay, so this is our in-sample accuracy, which means out of 10,000 images, it make 9,972 correctly. And if we try the out-of-sample, then the error rate is again around 2.1%.
Okay, so that is about the neural net. So it's about the Keras. So, any questions? If not, we'll take a break and we'll talk about the convolutional neural net later.